Okay, so we start with this lecture that is a permeability. The basic details are given. This is our 11:15 to 12:15 lecture. Uh, so just I will revise the first part. Already we discussed in our lecture quickly. We discuss about Darcy's law. So Darcy's law required basically a laminar flow for a saturated soil, and the velocity of the flow is proportional to the hydraulic gradient, so which I shown here. And so the velocity is equal to ki, so k is called the coefficient of permeability. If the sample of this permeability having a cross section area A, maybe small or capital, and if I multiply to this equation on both sides, so I can write in terms of discharge. Of course the discharge I consider as a unit discharge, okay, as KIA. Okay, so this is the basic part. Now here the I involved, which is called as a hydraulic gradient, and this hydraulic gradient is expressed using the basic concept in fluid mechanics, where we use a Bernoulli's principle. Okay, suppose this is the soil sample of length L. Okay, is subjected to two hydrostatic pressure at one end A at the center, and second hydrostatic pressure which is received here at point B. So from any one fixed line, datum line, the total pressure at A is calculated separately and total pressure at B is calculated. So total pressure at the A, which indicates the datum head by Z1, pressure head, okay, and velocity head is considered with 0 because the flow of velocity through the voids of a soil is very slow, and that's why this head is considered to be 0. Okay, similarly at the other end the total pressure is taken as datum head Z2, pressure head, and velocity head is 0. Okay, so this pressure required, this total pressure required to flow through the soil from point A to B to overcome its friction, then only it received in the point B, and during that there is a head loss. So you can see between the total H1 and H2 there is a head loss, which is the difference. So this head loss, if I determine by using a total discharge using a basic Bernoulli's principle, the total head at point A minus total head at point B, you'll find H is equal to H1 minus H2. Okay, because this bracket indicate total H1, this bracket indicate total H2, so difference is H1 minus H2. So this is the head loss. This head loss is H, which passed through the length L, then it is this ratio called as a hydraulic gradient I. So in the same figure you'll find that what is the stress at point A. The stress point at A is nothing but the pressure head multiplied by the gamma W, pressure head multiplied by the gamma W, and this is nothing but the P1, this get cancelled. Similarly the pressure head at point B, it means it was at pressure head A and pressure head at B. So you get these two stresses at point U1 and U2. These two stresses U1 and U2 called as a neutral stresses. Okay, so they are not because of any other external pressure, that's why we call it as a neutral stresses. because in the further the chapter, like in a shear strain, we are going to discuss about the pore pressure, which is beyond this neutral stresses. So in a Darcy's law, which we discussed, that what is K, V is proportional to K and V is equal to KIA. So K is called as the coefficient of permeability. So how do we define this K? So if you see is V is equal to Ki, and if I put I is equal to unity, then V is equal to K. So therefore we can write as average velocity of flow that occurs through the total cross-sectional area under a unit hydraulic gradient. So when I is 1, then you get V is equal to K. Now you'll find that the unit of K is similar to the unit of V. So therefore it can be a centimeter per second, meter per hour, meter per day, or sometime in an impervious soil is a meter per year also. So this is the basic about the K value. How long the validity of the Darcy's law takes place, which is further explained in this slide. Now you'll find that if I draw a proportional line between a seepage velocity and a hydraulic gradient, you can see the seepage velocity, okay, and hydraulic gradient. What is seepage velocity we'll discuss in the next article. In this 45-degree line, you'll find that after point L, so this graph deviates. Okay, the linear relationship ends at L, and the graph become a non-linear. So the critical point is L, which separate these two flow conditions. The first part is a laminar flow, so and second part is a turbulent flow. So at point L, when the discharge velocity, or sorry, seepage velocity is greater than critical velocity, then you'll find that when this V value is beyond this, then I is also greater than ICR. So I is greater than ICR. So it means on this side we get a turbulent flow, okay, and in a turbulent flow we can find out the velocity by a expression called as C into root of I. So the coefficient C depends upon a seepage medium, okay, whether it is a dense or a loose, etc., type of soil, whether sand or shrub, a clay, and turbidity of flow means the presence of a microparticle less than 2 micron particle. So these are the factor on which the C depends, and remaining part is the hydraulic gradient. Okay, so but in a laminar flow conditions it is a proportional, so therefore V is proportional to the I and V is equal to Ki. So the meaning is that the Darcy's law is valid only in the medium of a laminar flow where the velocity is less than, seepage velocity is less than critical velocity. So the next part, now we are going to discuss is another important one. Now, what is the difference between the discharge velocity and the difference between a seepage velocity? So earlier which we discussed that this V, velocity V, is called as a discharge velocity. Okay, and in the last graph we discussed that this is a seepage velocity. So when we write a Darcy's equation, the velocity can be considered as the average velocity. It can be also considered as a discharge velocity. So but what is the relation between these two, discharge velocity and the seepage velocity. Okay, so flow takes place through the total cross section area, that is A. It means if I consider a soil sample of cross section area A and a length L, and if it is subjected to the a discharge Q, then you'll find that the flow takes place through the total area A under a average discharge velocity V. But all of you know that what is the phase diagram, which consists of a solids and the voids. And the permeability means the flow takes place only through the voids. So it is not through the total cross section area responsible for a flow, but it is a void ratio. It is a void ratio in which the area of void responsible. So this section, which is considered of a cross section area A and a length L, is actual. Okay, and let us consider a theoretical cross section. Suppose just like a phase diagram. Okay, if I connect all the solids and put it into the two parts which is separated by a voids, just similar to the phase diagram, but voids I put it in the center. So this is a imaginary or theoretical diagram. If I take a section here, suppose it is a circular cross section. In that case, total cross section is A, and inside you will find the area of voids. So A is the total cross section, V is the average discharge velocity. In a theoretical diagram, AV is the area of voids, okay, and the velocity of flow takes place through the voids is definitely different, and therefore it is Vs, called as the seepage velocity. So we'll try to correlate between the V, discharge velocity, and the seepage velocity. Now all of you know the continuity equations. So therefore, if I consider these two are suppose a connected, then whatever the discharge will takes place to the actual diagram, same discharge will takes place to the theoretical diagram. Discharge will be the same. So therefore, in a continuity equation, if I take it is a area into velocity in actual diagram, and then area of voids into the seepage velocity. So if I equate this, then I can write, suppose in terms of this seepage velocity, then A divided by area of voids into discharge velocity. Now if L is the length, if I multiply and divide by the length of sample, okay, then I get the seepage velocity is equal to A into L, means this volume, whereas area of voids into L, I get the volume of voids only. So I had written these two very clearly. Capital V indicates the volume, small v indicates the velocity. And as we know from the basic relationship that the the porosity N is nothing but the volume of voids to the volume. So this ratio indicates it is 1 upon porosity. So therefore, seepage velocity is equal to discharge velocity divided by a porosity. Now, porosity, if you know the maximum limits for the porosity, because it is a porosity, you can see volume of voids to the total volume, and this is less than 1. So therefore this uh, n value is less than 1. So for example, if I take a uh, n is equal to 0.9, that is porosity is 0.9, and velocity discharge velocity, suppose I take it as 1 centimeter per second, then the seepage velocity, if I calculate by substituting these two values, 1 upon zero point 0.9, I get 1.11. So therefore, this indicates that the seepage velocity is always greater than the discharge velocity. That is, a velocity which flows through the voids is greater than the average velocity which flows through the total cross-section area. So this is the first part of the this relation, which in which we discuss about the relation between the velocity. Now, same we extend for the soil, considering a Darcy's law, okay, and which is in terms of a coefficient of permeability, which is when the flow takes place through the total uh, area A, and when flow takes place through the area of voids, that time the K, which we call it as a KP, which is called as a coefficient of permeability, coefficient of percolation, P for a percolation. It means it is through voids only. So here we can relate what is the K, coefficient of permeability, with respect to the coefficient of percolation, which is through the voids. So in a discharge velocity, if I write equation V is equal to Ki, similarly this is for actual, this is for the theoretical. Seepage velocity is it Vs is equal to Kp into I, and then if I take the a ratio this way, I remain same because the head loss takes place either in actual or theoretical is the same, and therefore the and length is fixed, so I remain same, so it get cancelled. So therefore this V upon the V upon Vs is equal to K upon K Kp. Okay, and in the last part, or the first earlier part, which we have seen that a Vs upon V also is equal to V upon total volume upon volume of voids. Okay, so ratio of Vs upon V is equal to volume of total volume upon volume of voids, which can also represent in terms of a porosity. So therefore here it is replaced, and it is substituted as this ratio is n from earlier, K upon Kp. So therefore if I write for a Kp, it is K upon small n. So again in example, if I take a n value as a porosity as a 0.9, and suppose K value I take it coefficient of permeability, suppose I take 1 centimeter per second. So again I get the ratio Kp, that is coefficient of permeability, is equal to 1.11. So this also shows that the coefficient of percolation, that is the flow takes place to the voids, is greater than coefficient of the permeability. So from this discussion, the two conclusions we can draw here, that the seepage velocity is greater than the average discharge velocity, and coefficient of percolation is greater than the a K value, that is coefficient of permeability. Okay, so this is the second part, and now we'll move to the determination of this coefficient of permeability. I hope all the groups have done this test and in a laboratory. So I'll be just explaining, not in detail about the preparation and all, because we have discussed and already conducted the experiment. So I'll be discussing about the basic of these two tests. So the coefficient of permeability can be determined in the laboratory as a falling head test method or a constant head test. Also can be determined in the field. Many times it is also important to determine the field, because it is the actual value we get it without any disturbance or other factor responsible for the change in K, which can be a pumping in test and pumping out test. So now we'll discuss about the laboratory test. The first laboratory test is the falling head test. In a falling head test, first we prepare a per meter which is filled with a soil sample. And now filling of the sample is as per the requirement of a soil properties. It depends upon the gamma value, depends upon the what is the moisture content. If the data is not available, then many times we fit this per meter mold with a maximum dry density and optimum moisture content, because the permeability is very much depends upon the void ratio. Okay, so after filling this, first the sample is saturated, this air vent which is shown here is open, and the water is passed to the sample until when we get a sufficient time for the soil to get fully saturated, then we can start the test. So it is a top, it is connected with a stand pipe. It is a small glass pipe. Diameter may varies from 10 to even the 20 So initially, suppose I fill this tube at a height of h1, which is measured at the bottommost part, or if I get a constant level, then from that, or generally from the in practice in a laboratory from the outlet. So one constant datum is taken. So we take a height h1 initially, and we start a stopwatch. So let the time is t1. And now as the time increases, so head drops from h1 to h2. At that time, uh, it the head drops to h2 in time t2. So this is a total head loss takes place from h1 to h2. Now let us consider a small head drop of dh which takes place in a small time t, small head loss dh in time t. At that time, the total head is h. This is for one moment we consider. You'll find that this dh or even this h decreases h1 to h2, but time increases from t1 to t2. So they are the inversely proportional. Okay. So let A is the cross section area of the soil sample inside the per meter. L is the length of the sample. A is the cross section area of the standpipe. H1 and H2 is the initial height, and the second one is the final height. H is the height at any particular instance when we consider small drop in a head in a time dt. So first we consider the flow through pipe, and then we consider the flow through soil. It is just like a two pipes connected in a series of a different cross section, but one pipe is filled with the water and second pipe is filled with the saturated soil. This is the basic difference. So in the first part we apply our the basic concept in the fluid mechanics, that is using the flow through standpipe is area into velocity. A is the cross section area of standpipe. This V we can write as a small drop in head in that small drop in time. This minus O is only because of the head decreases, time increases. That's why it is a minus. So from this, if I multiply the area, then I get a discharge. Q is equal to small a, that is area of standpipe, dH upon dt. uh, as we discussed earlier also, which is written here, that h1 head is greater than h2, but time t2 is greater than t1. So now we consider the flow through the permeator, that is through the soil, using a Darcy's law. Okay, so V is equal to Ki after multiplying area. Here Q is equal to Ki is H upon L into A. We are again considering that particular moment of dH and dt. So at that time, when there was a drop was dH, the total head from the bottom is H through a length of sample L in a cross section area of A. So equating these two equations, earlier equation of this Q, that is flow through pipe, and equating the equation uh, flow through the soil using Darcy's law, and rearranging the terms, taking the common term, this side is a dH, so I will take H on the right hand side and dt on the left hand side, other parameter on the left hand side. So I get minus dH upon H. So uh, on the left hand side you will get this all constants and dt, and other side is the terms in H. So above equation is for a small time dt, so when head drop was very small dH, and now for an entire head drop in our figure we have seen that we consider head drop or head loss from H1 to H2, initial to final, in a time or time elapsed was the T1 to T2, where T2 is greater than T1. So we integrate this equation to both sides. Left hand side is with respect to dt, so time T2 to T1. Right hand side is with respect to H, H2 to H1. By property of this integration, if I take eliminate minus, then this will get reverse, so H1 to H2 dH upon H. So the integration of the right hand side you will find is a log of H1 upon H2, and integration of dt, others are the constant, is substituting the limit T2 to T1. Therefore we can write unknown is the K, all other terms we know. Time is we know, area, both areas we know, length also we know, and head drop which we measure. So K is equal to, we get in the natural law, it is a function of H1 and H2 with other things are constants. Or similarly, K can be written in terms of a log to base 10 from multiplying factor 2.303 AL upon A. It is a time difference, time elapsed for a head drop H1 to H2. So this is the expression which we get from this falling head test called that is the K value. Now, what are the conditions in which this test can be performed, or this test is applicable for what type of the soil? So the falling head test is useful for a fine sand, silt, and the clays when head drop in a standpipe does not exceed to 1 centimeter per second. Meaning is that if I use a very permeable soil, highly permeable soil like a sand, uh, uh, particularly coarse sand, okay, or if I fill with the fine gravels, then the head drop from H1 to H2 will be so fast, it will be difficult to measure the time, and there will be the errors. So therefore the rate is controlled for this test as the 1 centimeter per second, then is it gives the best performance. So according to this, it can be used for the fine particles, including this fine sand, silt, and the clays. And you know the size of all this as per our IS IS standards. So this test is basically used when we call it as a soil, particularly as a impervious. I put in apostrophe. Okay, after certain values, say less than -6 or -8 centimeter per second, then it is an impervious soil. If you conduct this test for a clay, or conduct this for a highly permeable soil, then I get a difficulty in measurement in the H1 H2. Therefore, it is used for a impervious soils like a clay, where discharge measurement is a difficult, because you cannot collect a discharge, because it may give you a few drops or a few millimeter of water in a very large time, maybe 2 hours, 3 hours. Some clays gives you a certain 10 ml or 20 ml in 2 or 3 days, maybe 1 week, and there may be possibility of the temperature losses. So therefore, this method is useful for a fine sand, silt, and clay. So, what is the second method? If it is a highly permeable soil where we can measure a discharge, so for that we can use a constant head permeability test. So basically, this the soil sample preparations is the same. That is in the permeator with the required density, required moisture content. The sample is filled up and then it is fully saturated after running through a number of for a sufficient time. Generally, we observe here that when the head is a constant inflow and here is the outflow, then we say that the sample is saturated. You can open even the air vents frequently, release the air. So you'll find that here the stand pipe is connected with a tank, and this tank has an overflow pipe, and this is the inflow pipe. It means that when the water flows through the soil, the head will not drop because there is a continuous flow, and flow will not rise because of this overflow. So in this test, you are keeping the head is constant and you are measuring a discharge Q and what is the time required for the discharge. So let the A is the cross section of the soil sample, L is the length of the sample. So this constant head passes through the length, so it is I is equal to H by L. You are collecting a discharge capital Q in a time T, so I can write a rate of discharge as capital Q upon T also. So here very simple expression we can use according to Darcy's law. Now we need only to consider the flow through the soil, because there is no drop in the head, so it is only the flow through the soil which is given by Darcy's law. So therefore Q is equal to KIA. So I substitute Q is equal to capital Q upon T, H by L hydraulic gradient, and cross sectional area A. So therefore I can write K in terms of measured discharge in the time T, and the flow takes place through the length, through height H, and through a cross section area A. So just like earlier, this method is useful for a fine gravel, coarse sand, medium sand, and also for a clean fine sand, where the percentage of the fines, silt and clay, less than 5%, then that also can be used to determine the K. It means basically for a pervious soil where we can measure a discharge, for such soil we can use this test, okay, to determine the K. But if I take some soil which is at the interface, or you are trying to conduct both the experiment, keeping all the factors same, permeability will same. Permeability will not change, because there may be many methods to determine. Basically, the K value has to stay. But facility, this is a facility for a particular soil, that first method is used. For other soil, the second method is used. Now we'll try to solve a one simple example based on what we studied. Okay, so quickly I revise. And first we discuss about the falling head test, where we got these expressions. K is equal to 2.303 and other factors like a cross section area, length of sample, area of standpipe, time required, and head drop from H1 to H2. And just discuss the second method, that is constant head method. This is where we can find out K after measuring a discharge here in time T. The discharge passes through the length L and cross section area A through a constant head H. So here we try to solve one simple example. In this example, the area of sample is given, the details are given. Okay. So area of sample is given 100 centimeter square, length of sample is given 6 centimeter. Now the head drop is from 60 centimeter to 20 centimeter, that is H1, H2. Time required, let us say T1 was 0, so T2 was 5 minutes. So T2 minus T1 is a 5 minutes converted in 300 seconds. So area of standpipe is given as 2 centimeter square. So using the expression of the falling head permeability, we can find out K, writing these expressions and substituting all the values. That is small a given as 2 centimeter, you can see here 2 centimeter, then length of sample is 6, then the area, cross sectional area of sample is 100, time elapsed is 300, and which falls through a head from 60 centimeter to 20 centimeter. So the calculation gives me 4.395 10 raised to minus 4 centimeter per second. You can calculate in centimeter per minute. Okay, here I converted into a centimeter per second. This is the first answer. Now suppose I extend this problem in this way. If the same parameter is tested under a constant head and head is maintained suppose 18 centimeter, determine the total discharge. Either total discharge capital Q or even the small q. So the sample is same, parameter is same. First we conducted suppose H1 H and H2, that is falling head test, and now I am conducting in a constant head test. Okay, as I discussed earlier that K value remains same. Therefore using the K value, same K value, and a constant head maintain 18 centimeter, so we can write Q is equal to KIA, Q is equal to Q by T, K H by L A. Now substituting the values, that is K, which is just now we got it as 4.395, constant head which is measured is 18 centimeter, through a length is the same 6 centimeter, and area is also same 100 centimeter, 100 centimeter square. So you get a discharge as a time rate discharge 0.1385 centimeter cube per second, or multiplying the time you get 39.55 centimeter cube. So this is how a simple calculations can be done to determine the K value. Further also we'll see some little bit more difficult problems. This is a simple practice problem. And now this is the problem for your exercise. So this problem based on, as we discussed this two method. So all the details are given here, and here the question is slightly different. In this case, the the perimeter length is given, cross-sectional area is given, and the method is used to determine the K. Here directly the name of method is not given, but you can guess from the further. And it is expected that this K value, as we have written the expression for K, so here the K is given, the target is given 1 into 10 to the power minus 4 centimeter per second, and head in the standpipe falls from a 30 centimeter to 10 centimeter, mean H1 and H2 is given in time 40 minutes. So this clearly shows that it is a falling head method. So using the same expression, in that expression only the area of standpipe is unknown. So you first calculate the area of standpipe, and then from area calculate the diameter of the standpipe. So what I suggest that you try to solve today, take your own time and send it me on my the email. I will forward the instruction how to save it and send it to me or the MTech student. So this problem you solve it by your own handwriting. Okay, whatever the answer you get it, okay, maybe the correct or maybe with mistake, no issue, but you try and send me. So your email will indicate that you have participated in this class and discussion, and also you are involved in solving this problem. So try to solve this take your time and send it me. Okay, the further instructions I will give you. Okay, so our next lecture will be in the next week, and I will come back to that time. Thank you.